Okay. Okay, so it's my great pleasure to introduce Mariusz Mirek. Mariusz Mirek is a professor at Rutgers University and at the University of Wrocław. His primary focus is in research is understanding phenomena of convergence in analysis and in ergodic theory. There is a lot of Fourier analysis, additive combinatorics, number theory, and probability behind. Mariusz obtained his PhD in 2011 at the University of Wrocław under my supervision. And 5 years later, he got habilitation at the University of Bonn. And after a PhD, he had postdoc positions at the University of Bonn, at the Institute of Advanced Study in Princeton, and also at King's College London. And Mariusz has a lot of papers, but in particular 4 papers with Mariusz Wróbel, our colleague from Wrocław, and with 2 mathematical giants, Jean Bourgain and Eli Stein. And one of them is published in American Journal of Mathematics, which is top of the top. And 3 other also in a topical journal, Geometric Aspects of Harmonic Analysis. And they proved dimension-free estimates for Hardy-Littlewood maximal functions. And this was a new result in, let's say, a result that that made a breakthrough and opened possibilities to solve many problems that stayed unsolved for a few decades. Mariusz obtained a number of grants and awards, in particular the Wacław Sierpiński Prize of the 3rd Division of Polish Academy of Science, which is given to young mathematicians under 40 years old for their outstanding achievements in mathematics. And the prize is highly competitive. Okay, Mariusz, Zoom is yours, please.
Okay, thank you, Eva, for this introduction. It's a great pleasure for me to be here to speak at this conference. So today, I would like to give you a survey about interactions of Fourier analysis and ergodic theory and additive combinatorics. So let me start from, okay, so let me see. Okay, so let me start from very beginning, from 1936, when Erdős and Turan so realized that it might be possible to find arithmetic progressions of arbitrary length in any sufficiently dense set of integers. So so where the density here in this problem is defined not in the topological way, but in the sense of the upper Banach density, so which is the quantity of this form. So we consider a subset of integers and we take a look at the number of elements inside the block between 1 and n. And so we divide the cardinality of this set by n, and we ask about the lim sup. And it's important for this lim sup to be positive. If this is positive, then the Erdős and Turan conjecture asserts that there should be arithmetic progressions. In fact, infinitely many arithmetic progressions inside this set E. So in other words, this can be precisely stated in the following way. So we consider a subset of integers, which has positive upper Banach density. So which means that this quantity is positive. And then for any integer, we expect that there are infinitely many arithmetic progressions of this form. By the arithmetic progressions, we consider the configurations of this form. So we start from point x, x plus n, x plus 2n, and so on. So here, so this says that we have arithmetic progression of length k plus 1 inside E, and the conjecture asserts that this happens infinitely many times. So I have to say that, that was, you can imagine that was 1936, and so then at that time, additive combinatorics were developed by those two guys. So every time when I think about this conjecture, about this statement, so it's very surprising to me to formulate the statement of this form, because so we start from very mild assumptions. So this is the assumption that we consider subset of integers with positive upper Banach density. It's very mild. It says nothing about the structure of this set, but on the other hand, we are able to deduce very strong statement that the set of integers with this property, it has completely non-arithmetic. This is completely non-arithmetic assumption, and we can say something about the structure of this set. In other words, that the set of integers with positive upper Banach density inherits the additive structure from the set of integers in the set of the existence of this patterns of this configurations inside. So, and here let me give you some number of examples where this upper Banach density can be calculated. So if we consider, of course, arithmetic progression with spacing Q, then it's obvious that this upper Banach density, it's equal 1 over Q. On the other hand, if we consider the set of prime numbers, then it has vanishing Banach density because of the prime number theorem. So we know that this quantity asymptotically behaves like n over log n. So this is a famous result from number theory. But this, what completely destroyed my intuition about this problem. So this is the set of all square free integers. So if we consider the set of square free integers, so this is the set of integers where we remove all squares and all multiple of squares. So this is the set. So for instance, 10 is square free, but 12 is not square free because 4 can be represented as 2 to power 2. And then if we use a little bit of Fourier analysis or a little bit of probability theory, we can show that the upper Banach density in this case is equal to 6 over pi square. So this is definitely positive number. And here it's difficult to imagine that the configurations of this form may exist inside this set. So because the squares, if we remove the squares, so the squares have this the set of squares has this property that if we consider squares for 2 consecutive squares for large n, then the gaps tends to infinity. So we remove. So this what remains after removing the square free integers. It's a very weird set. Okay, so that's the conjecture. And now let me tell you about the current state of the art. So in 1953, Klaus Roth, he was able to prove Erdős-Turan conjecture in the case of arithmetic progressions of length 3. So that was, and he used the classical Fourier methods to prove this this conjecture. It's a very beautiful proof. Now we have many variants of this proof. I will tell you how to use Fourier analysis in a moment to attack this problem in the context of arithmetic progressions of length 3. And that was 1953. And 20 years later, André Semeredi, so he solved the conjecture of Erdős and Turan in full generality. So he was able to show that if we consider a subset of integers with positive upper Banach density, therefore any integer bigger or equal to, there are infinitely many arithmetic progressions. So in other words, the configurations of this form. And that was Semeredi. So Semeredi used in his proof very intricate arguments from combinatorics and graph theory. All methods were elementary, though very intricate. And this what left, and what is famous these days, what left from Semeredi's proof and what is important in additive combinatorics is something which is called the regularity lemma in combinatorics. So it's a very important tool for people in combinatorics. But you know, that was also a starting point for Furstenberg to start to think about this problem. And Harry Furstenberg in 1977 of the previous century, he got completely different idea to prove Semeredi's theorem. He used tools from ergodic theory, so he used ergodic methods, and he gave a conceptually new proof of Semeredi theorem using something which is called today the multiple recurrence theorem. In a moment, I will tell you what the multiple recurrence theorem is. And also in 2001, Tim Gowers gave a new quantitative form of Semeredi theorem, which is much more in spirit of Roth theorem. And he developed something which is called the higher order Fourier analysis. So I will give you tell you what, so let me tell you what, in fact, these guys did more precisely. So here we have quantitative formulations of Semeredi's theorem. So in fact, you know, if we consider a function Rkn, and this function denote the size of the largest subset of integers from 1 to n, containing no configuration of this form, which does not contain arithmetic progressions of length k, then we can quantify the behavior of this function from above. And in fact, you know, this is what Klaus Roth proved in 1953 using classical Fourier methods. It was the following upper bound for this function in the case of arithmetic progressions of length 3. So he showed that this function behaves like n over log n. And so, but you know, on the other hand, either Semeredi or Furstenberg, they proofs give only that this function Rkn behaves like small o of n. So, and the reason is that, so in Semeredi's approach, so he used van der Waerden theorem, which on the other hand use in the proof requires axiom of choice. Furstenberg also, the Furstenberg's approach also used the axiom of choice in his argument. So therefore, this is the reason why we have this. And that was the starting point for Tim Gowers, who wanted to understand if this function can be estimated from above in the context of arbitrary long arithmetic progressions. And in 2001, he came up with a beautiful idea, which these days, so he developed a huge theory, which these days is called the higher order Fourier analysis. And he was able to show that this function, it behaves like n over log n to gamma k. And this quantity gamma k can be quantified in the sense that this is usually, it's of the form 1 over 2 raised to a large power. And this large power, it's a big number, it's a huge number, and it usually reflects how many times the Cauchy-Schwarz inequality was used in the argument. And so that's so this is and this can be described explicitly. Okay, so and now let me give you an idea how to prove Roth's theorem using Fourier analysis. So the idea is absolutely beautiful. But for this purpose, we have to reformulate a little bit the Roth theorem. And so we, in fact, you know, it's in these problems that arise in additive combinatorics, it's useful to work on the finite set of integers. So usually on the cyclic group instead of set of integers, because then, you know, the Fourier analytic tools are very nice, you know. So we work with finite exponential sums, and in other words, you know, the Fourier analysis on the finite abelian group, it's very pleasant. So, and the Roth theorem can be reformulated in this way. So for every delta, there exists an integer such that for every subset in the cyclic group Zn, which satisfies this property that the cardinality of A is bigger than delta n, contains AP3, which means that it contains an arithmetic progressions of length 3. And so let me explain how to marriage Fourier analysis with problem that, you know, has a purely combinatorial formulation. So this is what we do. Okay, let me recall that, or introduce for you the definition of Fourier transform on the set Zn. So this is the exponential sum multiplied by the Fourier characters, and which is normalized. So we work, in other words, with the counting probability measure. And so this denotes the finite Fourier transform for a function f on Zn. So let's call the quantity the zero Fourier coefficient of the characteristic function of A to be alpha. So it's clear that alpha, this quantity, is bigger than delta, because in other words, you know, this is the cardinality of A divided by n. So this is what this quantity precisely is. So therefore it's bigger than delta from this assumption that we have here. And now, so we are interested in showing that this quantity, this counting function, so this is the, so we are interested in counting all pairs which have the property that A, A plus D, A plus 2D belong to A. So in other words, if we show that this normalized function here, normalized counting function, is non-zero, then we will know that we have arithmetic progressions of length 3 inside A. And now you can observe that this function here can be rewritten in this form. So that's like a double sum corresponding to the characteristic function over characteristic function corresponding to the set A. And now you can see that so if we use this this formula for Fourier transform and the Fourier inversion formula, then this quantity can be rewritten in this form. So in other words, we get zero Fourier coefficients plus Fourier coefficients that correspond to non-zero frequencies. And so, and this quantity provides some important information. So usually in Fourier analysis, what happens, you know, if we ask about the asymptotic behavior of the, you know, of the quantities of this form, they are usually, you know, incorporated in the zero Fourier coefficient. So this is where the asymptotic formula is usually hidden, I would say. And the rest, so the quantities that correspond to non-zero Fourier coefficients, they are negligible. They are usually, you know, they decay. They have some additional decay, which produce a quantity which is of smaller order compared to the zero Fourier coefficients. And this is what we expect here. So this is intuition that comes from Fourier analysis. And now, you know, if we take a look at the left-hand side here, so this expression, so we can think there is a very nice probabilistic intuition about this formula, about this what we get here. So, and this probabilistic interpretation means that, so the left-hand side, so this is, in other words, what we have here. So this is the probability that variables x, y, and z all belong to the set A if you choose them randomly to satisfy this equation, okay? And now without the constraint that x plus y is equal to z, this constraint comes from the fact that, we are looking for the arithmetic progressions of length 3.
Mariusz,
So this
excuse me, Mariusz,
yes.
I don't understand. What do you use to switch from indicators to Fourier transforms of indicators? Some kind of Planck?
Yeah. Okay. This is what we have done is that we use the Fourier inversion formula, that if you apply Fourier transform and the inverse Fourier transform to function, then you recover your function.
Okay.
So in other words, here you see that we applied that this function here. So you can think that this is Fourier transform, and you apply again inverse Fourier transform. And if you calculate the inverse Fourier transform, then you get exactly this, what you have here. This is a little bit of argument that is needed to pass from this. But this is the Fourier inversion formula.
Okay, thank you.
But what is more important, to understand what happened here is the fact, this probabilistic intuition that lies behind of this problem. So if we take a look at this expression, if we forget about this constraint that x plus y is equal to z, so this probability would be alpha cubed. And since each of the variables x, y, and z would have a probability alpha of belonging to the set A. And this is what we expect to be the correct asymptotic formula for this quantity. So therefore, the term alpha cubed on the right-hand side can be thought as what one would expect, whereas the remainder, the blue formula, the blue quantity, is a measure of the effect of the dependence of variables x, y, and z on each other. And this is negligible. So in the end, if we use a little bit of, so in fact, the proof now from now on is to show that this blue quantity is much smaller than alpha cubed. And so for this purpose, one has to use pigeonhole principle and estimates for the exponential sums, which are reduced to, calculating certain geometric sequence, estimating certain geometric sequence. And so if we put things together, then essentially we can show that this is of the smaller order term. So that's how the proof goes. But here, I wanted to show you this small calculation because it shows, the passage from a problem which is purely combinatorial to a problem. So here you see that what is important, this function here is positive. So this is what we do. We pass from positive function to something that oscillates. This function, for instance, has signs. It takes signs plus and minus, so it's not negative. So in fact, this is what we do. We do something, crazy because, so we replace function which is positive. This is what we usually like to function which has signs. But, the properties, orthogonalities that, can be detected using Fourier tools allows us to say that this is small. And this is the usual philosophy in problems in combinatorics or additive number theory or analytic number theory when we use we start with problems which have positive nature, and we use Fourier analysis to say something interesting about the ultimate, about the problem or difficulties that arise in question. Okay, so this is what I wanted to say about Roth. And now let me tell you what is the current state of the art, because the Roth theorem was a starting point of a huge business in additive number theory. So Roth proved that the function R3 of n behaves like n over log n. And there, this was improved by Heath Brown, by Semeredi. Bourgain did a lot of efforts, to understand this. So, and there is an important paper of Bourgain from 2008, where he introduced new tools, to attack this problem. And so one of the tools, it was something which is so he used the Bohr sets to understand this kind of set. So this is a very important paper. And then Tim Sanders in 2010, he was able to show that this quantity behaves like, so he was able to break this polynomial dependence here and replace with this logarithmic. And then, so that was the famous annals paper of Sanders. And then there were some there was some improvement of Thomas Bloom, and recently also of Tomek Schoen, who obtained this. And a recent breakthrough of Thomas Bloom and all of CSASC, they broke the barrier. They showed that this behaves like n over log n to 1 plus c for certain c. And this paper shows, for instance, that the set of integers, if we use this theorem, it shows, for instance, that if we consider the set of inside the set of prime numbers, if we ask about the existence of arithmetic progressions, then this can be deduced from this theorem. So which before was not available. I will tell you about the arithmetic progressions inside primes in a moment. And this paper of Bloom and CSASC was inspired by ideas of Schoen. So Schoen, he did some some important observations, and he introduced important ideas in this paper, and that's which were used, to push the things further by Bloom and CSASC. So that was important result. But on the other hand, if we ask about the lower bound for this function R3 of n, so there is an older beautiful results of Berendt from 1946, who showed that this function from below should behave like this. So it's a very elementary argument which is reduced to some question about the linear independence on the circle, and so this lower bound. So, and now you see that this what we have here, and it's very far from this what we have on the as the lower bound. So it's so still we are very far from this number, and so who knows, maybe at some point, but at this moment it's not. It seems that that some completely new ideas would be required, to understand, think further. Okay, so now, and now let me start change the subject a little bit and introduce the concepts from ergodic theory. So let me tell you what the measure preserving system is. So we will consider a measure preserving system. So this is usually a sigma finite measure space, which will be equipped with a measurable mapping here, T, that acts on X, takes values in itself, which preserves measures. So which means that the following equation is satisfied for every measurable set. And so here we have some bunch of examples. So from the point of view of pointwise convergence problems that I'm interested in, the most important dynamical system, this is the integer shift system. So this is the set of integers with the sigma algebra of all subsets of Z, the counting measure, and the shift operator, which is defined in this way. So we take an integer and we, so we obtain x plus 1 or x minus 1 depending on the context. So, and this is the shift operator. This is how the shift operator is defined. So, and I will tell you about this, why it's important in a moment when I formulate what the pointwise convergence means in ergodic theory and what kind of objects we will study. And so another important example that gives some intuition is the circle rotation problem. So so this is the torus with the Lebesgue measure and rotational map. So the rotation about an irrational angle. So this is x plus alpha considered modulo 1. So which means that the addition is considered on the torus. So here is important that alpha is irrational. And this dynamical system is important from the point of view of equidistribution problems that arise in number theory.
Sorry, may I have a question?
Sure.
So do you really need this assumption that this alpha is irrational in order to have something which is measure preserving?
Yeah, okay. So no,
different, but
No. You're right. So we, in order to show that this is measure preserving, we don't need irrationality. I agree, but you know, but you know, if alpha is rational in all problems that arise in ergodic theory, you know, this is not interesting problem, because you know, then your dynamical system is finite, the orbit is finite. So we like when the orbit is infinite. So therefore, we ask about. We will always assume that alpha is irrational. So, and we have also the circle doubling system. So this is another system on the torus with Lebesgue algebra and the doubling map. So this is the multiplication by 2. So this is the system that allows you, for instance, establish the Borel isomorphism between the set of the unit interval on the real line and the Cantor set. So which is the set of all infinite binary sequences.
And I have one question. Will I broke something when in the integer shift system I replace the 1 with another integer, like, I don't know, 2, 3 or something? Because it, for me, it don't look like this, but I may be wrong.
No, yeah, you are right. So we can replace by any other integer.
Okay, but I suppose for theoretical reasons, this +1 will be important.
Yeah, it's important because we will take a look at the iterations of S, and then if you take the power of S, then we want to be able to produce all integers.
Aha, okay, thank you very
much. Therefore,
much.
Therefore we consider the shift by 1. And we have also the continued fraction system. So this is the unit interval with the Lebesgue measure and the Gauss measure, which is the Lebesgue measure with the following density. This quantity is normalized to have mass 1. It's a probability measure. And the continued fraction map is defined. This is T of x equal to 1 over x, understood modulo 1.
So I have one more question.
Sure.
So regarding this circle doubling systems, do this map really preserve the measure?
Yes. This map preserves the measure, but in order to see this, one has to draw a picture. This is the best way, to draw a picture and to see what happens. So this requires a little bit of a small argument. But
okay,
yeah.
So this is like taking a square of a complex number, but you take a pre-image, yes? So this is the reason.
Yes. Because you take not. So here is important that measure preserving, you take the pre-image. Yes. Otherwise, it doesn't satisfy this.
Okay. I now see. Thank you.
Yeah. And in the continued fraction system, so if you take a real number from the unit interval 0, 1, and you consider the continued fraction expansion, and you take a look at the nth digit, so that the nth digit can be seen as the nth iteration of this continued fraction map. So it's a very useful way of thinking about the continued fraction. They can be seen as certain dynamical systems, and in some problems, it's important to have this description. So it's a very nice problem. Very nice example, Okay, so and now I would like to tell you about the ideas of Furstenberg. So Furstenberg ideas to attack Summarelli theorem was so he was able to see a link between Summarelli theorem and the Poincaré recurrence theorem. So the Poincaré recurrence theorem, so it's a theorem that was stated in 1890, and it says that if we have a dynamical system which is finite, and we consider a measurable subset with positive measure, then the measure of this quantity is non-zero, and it happens infinitely many times. So in other words, we have the so what's the meaning of this? So in other words, we take an element from X, we consider the orbits of this element and under map T, and we ask how many times this orbits returns to the set E. So in other words, so this is some recurrence theorem. So we want to see how many times point T returns to our original set, to the set E, under the iteration by T. So, and it has, this problem has a very nice physical interpretation, which can be stated as follows. So if a cloud of gas, which is initially confined in the left compartment of a vessel, is released into the right empty compartment, then after a sufficiently long time, the gas particles will return to the left compartment. So in other words, if you split your auditorium into two rooms, and you will have blue gas in one part, and the other part will be empty, and you destroy the wall, then the gas particles start to move. But after some time, Poincare recurrence theorem says then these particles will return to the room where they initially stayed. So that's the, and moreover, Poincare recurrence theorem says that it will happen infinitely many times. We don't know what is the first time of this phenomenon, but it will happen infinitely many times. And Furstenberg realized that maybe it's possible to extend the Poincare recurrence theorem to something which he calls the multiple recurrence theorem. And maybe it's possible to prove something like this, that if we start with a finite dynamical system, we consider a subset, measurable set with positive measure, maybe it's possible to prove some statement of this form for some integer. So, and now let me give you a link between this statement and the Semeradi theorem. So what do? So let's consider a subset of integers which has positive upper Banach density. And then for any integer k, we are looking for these configurations, because that are arithmetic progressions. And so now we can see that each point here can be interpreted as appropriate power of your starting point under the shift iteration, under the shift operator. So which is Sx equal x plus 1. So in other words, this point x plus 2n, this is S to n acting on x, and so on. So therefore we see that this can be, so now we have dynamical system interpretation of this. And now it suffices to show that if this set is non-empty, then we are done. We have arithmetic progression of length k plus 1 in this case. So therefore, if we could prove this multiple recurrence theorem for the set of integers, it would be great. But there is one point that the Poincare, neither Poincare recurrence theorem nor this theorem are not true in the infinite dynamical systems. So we cannot drop this assumption that measure space is, the underlying measure space is finite. So it cannot be done. But still, Furstenberg, so that was a brilliant idea. So he established the Poincare recurrence theorem for the finite dynamical system. So he was able to prove the following theorem. So he said that if we have a dynamical system, probability measure, corresponding to a probability measure, and if we take any subset, measurable subset with positive measure, then the following quantity is positive. So therefore, in particular, this implies, so he proved a stronger statement, which in particular implies the recurrence theorem, multiple recurrence theorem that holds for infinitely many integers. But now this is for finite dynamical system, but we want to use this for infinite dynamical system, for the set of integers, if we want to have a satisfactory answer, if we want to solve the Semeradi theorem. But so Furstenberg also figure out something which in the literature is called the Furstenberg correspondence principle. It's a bridge between, you know, problems between ergodic theory and problems in additive combinatorics. And this bridge can be formulated as the following.
Mariusz,
Yes.
You said that. So how do we skip the assumption of finite measure?
Yeah. Now I want
the measure is in Furstenberg still is probability measure.
Yeah, that's right. Now I want to explain how to do this. So this is this is what I'm saying. This is the Furstenberg correspondence principle, which, as I said, this is a bridge between the problems in ergodic theory and combinatorics, and it has the following formulation. So we consider a subset of integers with positive upper Banach density, and now Furstenberg claimed that there exists a probability measure preserving system, a new system, which is probabilistic. It's important that it has the total mass of our space is finite. So that for any measurable set in X, and there is a, sorry. Okay, so let me put it, let me state it one more time. So we start from a set of integers with positive upper Banach density. And then there exists a probabilistic measure preserving system, a new system, and a measurable set with the property that the measure of this set is the density of the set A. And moreover, we have the following inequality, that measure of this set is dominated by the density of this set, where S here, this is the shift operator on the set of integers. Okay, so here we have density function. So, and now, so the Furstenberg principle allows us to formulate, to pass from the set of integers to a probabilistic measure preserving system. So now we have a set E with this property that the measure of E is equal to D of A. If this density is positive, then the measure of this set is positive. Now using Furstenberg theorem, we can prove that we have multiple recurrence theorem, which means that the measure of this set is positive. And the correspondence principle, again, furthermore, it has this bound that density from below is estimated by the measure of this set, which is positive. So therefore, density of this set is positive. If this density is positive, then this set cannot be empty. And now we have the theorem that in A there are arithmetic progressions of length k plus 1 here. So that was the Furstenberg idea. And and in fact, this correspondence principle is not difficult. So this is what we do. So we interpret, this is like in the theorem when we prove, when you show that the set, the subset of all, so the cardinality of the subset of all integers is the same as the cardinality of the Cantor set, the set of all binary infinite sequences. So this is what you do. So for every subset of integers A, you associate a characteristic function of A, which takes values 0 and 1. And this determines the one-to-one correspondence. And this is how Furstenberg constructed this, thought about this problem. So he used exactly the same idea. He constructed, so he used this, so he, instead of thinking about the set of integers, he started to think about the characteristic function of the subset of integers in the Cantor set. And the Cantor set, so if we, on the Cantor set, if we have Borel measure, then, this is, and, we have a natural Borel measure on the Cantor set, the canonical one. So, okay. And this is.
Sorry, may I ask a question?
Sure.
So do I understand it correctly that this dynamical probability measure preserving system is just Cantor set with the standard sigma algebra of Borel sets, and with in fact Haar measure, yes? That this is something like a Haar measure.
Yeah. Okay. So this is more subtle, but yeah, but you know, but your dynamical system, this is the Cantor set with the classical with the corresponding Borel sigma algebra. Yeah.
So in other words, this dynamical system does not depend from A. What depends from A is this particular set E.
This measurable set E. That's correct.
Mm-hmm. Okay, thank you.
Yeah. Okay. So, but I just, I wanted to tell you, what is the idea that, the set of instead of thinking about the set of the integers itself, we think about, the characteristic function of subset of integers. And now we can interpret, everything lives in the Cantor set. And this is what makes, this is compact space. And this is what makes our life easier and allows, Furstenberg, to pay attention on this theorem, which is the most important thing. Okay, so, and now let me tell you about the further development. So Furstenberg proof of similarity theorem was a major breakthrough in modern ergodic theory. And, one of the generalization, it's a famous result of Bergelson and Liebman from 1996, which allows us to consider polynomial configurations, which is completely unclear if such a configuration may exist in the subset of integers with non-vanishing Banach density. So if we consider polynomials with integer coefficients with zero constant term, suppose that we have probabilistic dynamical system and we consider measurable set with positive measure, then Bergelson and Liebman were able to prove the following, that this lim-inf corresponding to this average is non-vanishing. So in particular, if we use this, then we have polynomial multiple recurrence theorem, which implies that the subset of integers with non-vanishing Banach density contain polynomial patterns of this form. So this is completely non-obvious result, but we have it happens in the set of integers with positive Banach density. So in other words, the set of positive Banach density, the subset of integers with positive upper Banach density, they have they have blocks that inherit very particular structure from the set of integers. So they cannot be completely irregular in some sense. So okay, so and now let me go further. And here we have, so the similarity, the Furstenberg result was also important to prove Green-Tao theorem, famous Green-Tao theorem, which says that there are arbitrary long arithmetic progressions inside the set of prime numbers. So as we have seen, we know that the set of prime numbers has vanishing Banach density because of the prime number theorem. So we cannot appeal directly to similarity theorem to deduce this result. But in 2004, Green and Tao were able to use the methods, the ideas from Similarity's proof, and in fact, the ideas from Gauer's proof using the higher order Fourier analysis, and derive this result. So now the positive upper Banach density is considered inside of the prime numbers. So in other words, we consider the relative upper Banach density. And if this is non-zero, then we have arbitrary long arithmetic progressions inside E. And so Green and Tao theorem was also important because it has all this theorem that I mentioned. They have existential nature. So they only say that we have arithmetic progressions inside those sets. But we don't have any reasonable algorithm to find those arithmetic progressions. And so it seems that there is a huge business where people started, to think about efficient algorithms to construct arithmetic progressions inside the primes. And now it turns out that the longest and largest known arithmetic progressions inside primes, this is AP27, which was found 3 years ago by Rob Gahan. And so this is the quantity of this form. So it's a big number. And but but I would like to emphasize one thing, that in 2007, that was essentially when I started my PhD. Jarek Wróblewski started, to try to find arithmetic progressions inside primes. And he found an arithmetic progression of length 24. And so for this purpose, he used 75 computers in our laboratory at the University of Wrocław. So with the following hardware. So here you have listed. But a few years later, Sony PlayStation 3 was advertised. And the software of Wróblewski was implemented to this Sony PlayStation 3, and one machine was sufficient, to find AP26 of this form. So that was a huge technological jump, in this business. And people are now, fascinated with finding, this efficient algorithms that would allow, to establish the APK inside primes. This is also related to a problem of searching large prime numbers, so that's also people construct efficient algorithm, that would allow us to find it. So that's a digression that, that this theoretical green tau or Semeredi are also important from people from computer sciences to establish this kind of things.
Sorry,
And yes.
Sorry, could we go back to the slide?
Sure.
The previous slide. So in all these three coefficients, there is some factor which is the same, yes? It's 2, 2, 3, 0, 9.
Yeah, that's right. That's right. So this is you see that this factor, it's it's the same. And I think that, as far as I remember, I cannot tell you for sure, but this is double factorial of certain number, as far as I remember. But you can check this on the internet, browse this easily on the internet, and you will see how where does this number arise, Okay, so and now let me tell you also about some other contribution. So a few years ago, I got fascinated with this kind of problems with existence of arithmetic progressions. And when I learned about green tau, at the same time, I learned about something which is called the Piasecki-Shapiro prime. So this is the subset of primes, which is of this form. So we take the primes and we take the integers of this form, and we take a look at the intersection, and we take a look at the primes which have this form. And Piasecki-Shapiro in 1953 was able to establish the asymptotic formula, the prime number theorem, the counterpart of the prime number theorem for the Piasecki-Shapiro primes. So he was able to show that this asymptotically behaves like n to gamma over log n. And for this kind of gamma. And and I started to think about the existence of the arithmetic progressions inside this Piasecki-Shapiro primes, because this is not settled by neither green tau or green theorem, which was established for the prime number for the AP3 inside the primes. And it turns out that if you take a little bit worse gamma here, which is of this form, then and consider a subset of Piasecki-Shapiro primes which have relative upper Banach density, so this quantity is positive, then they have non-trivial arithmetic progressions of length 3. And here, for in order to prove this theorem, I used some methods from Fourier analysis, and I was able to derive, this kind of results. So in other words, the conclusion is that one can go below, one can decrease and decrease this density, in other words, one can consider sparser subset of primes, and still there is some hope that you can prove existence of arithmetic progressions. It's not clear at the moment what is the lower bound for this, but if they have some reasonable structure, then you can say something like this. Okay, and now let me go back to the ergodic average. So I think that my time is running out. But I will keep going. So ergodic averages. This is an important tool to detect recurrence points. So in other words, if we understand the behavior of this averaging operator, limiting behavior as n goes to infinity of this averaging operator, then we can say something about the recurrent points. So in other words, if we apply our averaging operator to the characteristic function, that this is a counting function that allows us to count the number of visits of t and x inside E. And normal pointwise convergence for an can be used to reprove the Poincare recurrence theorem, so which we remember is the statement of this formula: probability measure preserving system. For every set with positive measure, we have that the measure of this set is positive for infinitely many integers. And in the early 30s of the previous century, von Neumann and at the same time Berkhoff proved pointwise and norm convergence for this averaging operator, ergodic averaging operator. So this is the statement of this form, that for every function in LP, which is P integrable, there exists another function, a limit, a P integrable function, such that the limit of an as n goes to infinity is equal to f star for almost every x and in LP norm. And now let me tell you how the proof goes. So this is usually, so there are many proofs of this, but one which is particularly important from the point of view of this, what these days happens in ergodic theory and in pointwise convergence problems. This is the proof which is based on the two-step procedure. So first we have to establish quantitative version of ergodic theorem, which is usually the maximal inequality. So we have to show that for P between 1 and infinity, we have this maximal inequality. And this, there is some nice transference principle that allows us to, which is called the Calderon transference principle, which allows us to pass from the set of, from the dynamical system to arbitrary dynamical system to the set of integers. And so instead of working with this set, we can work on the set of integers on Z. And so which is much more pleasant because the structure of Z, okay, here there should be Z. Because the structure of the set of integers is much nicer. And so it suffices to prove this inequality. And this follows from the hard, this is in fact, hard related maximal inequality that was proved in 1920s. And here you see that if we put if we consider Tx equal x, this is our measure preserving transformation, we plug this here, then we immediately obtain this operator. But now the converse is very nice, and it says that if we have this inequality, then for any dynamical systems, we may have this inequality with the same implicit constant as we have here. So that's the first step. And this step allows us to say that the set of all functions in LP for which we have pointwise convergence is closed in LP. So therefore, in order to obtain the pointwise convergence on all LP spaces, we have to find a dense class of functions for which we have pointwise convergence. And here we can use something which is called, sometimes it's called the von Neumann trick, but in fact, this is the Riesz decomposition. So this is what we do. Let's start from L2 space, because this is a Hilbert space. And let's consider functions on L2 which are T invariant, so that they're functions of this form. If we apply our averaging operator to the T invariant functions, this is the identity operator. So we have pointwise convergence. There is nothing to do. And now we have to understand the orthogonal complement of this set. And it turns out that, therefore, we work with Hilbert spaces. And if we consider, it turns out that this orthogonal complement to T invariant functions on L2, this is the closure in L2 of the space of this form, the functions G composed with T minus G, where G is a bounded square integrable function. And then if we take function f, which is here, and apply our averaging operator, then this averaging operator telescopes. Only the first and the last term may survive. And because this is a bounded function, if we divide by n, then this tends to 0 as n goes to infinity. So we have almost everywhere convergence on this part of our Hilbert space to 0. So therefore, we are done. And now, because this space, the algebraic sum is dense in L2, so we have pointwise convergence, not dense. So this is essentially, the proof of the Birkhoff-ergodic theorem. So very, very quick proof. And this also, gives us a strategy how to proceed, with more general operators. And there was a question in 1980s of Bellow and Furstenberg. They asked independently about the pointwise convergence for the averaging operators, but now, when the orbit are taken along polynomials. This is a polynomial with integer coefficients of degree bigger than 1. And Furstenberg asked this question because he was motivated by a result of Sarkozy, which says that if we consider any subset of integers with upper Banach density, then there are configurations of this form x plus n squared. In other words, we can find in subset S two integers whose difference is a perfect square. And Furstenberg used, in fact, here norm convergence to deduce the polynomial Poincare recurrence theorem. And he was able to show that, under the assumptions of Poincare recurrence theorem, for any polynomial with integer coefficients, we have this conclusion that this set has positive measure if we start with a measurable set with positive measure. And the question about pointwise convergence turned out to be very difficult, and even for the squares. And the reason is that because here we have, if we take a look at the consecutive squares, then the difference is an unbounded function. So in other words, the squares have unbounded gaps as n goes to infinity. And we cannot use this trick from the previous slide to establish pointwise convergence on a dense class, because it does not telescopes. But Bourgain was able to use the ideas from the circle method of Hardy and Litwood to establish LP boundedness of the maximal function corresponding to this operator, and instead of and to prove pointwise convergence, he was able to show the following square function estimate. So here is important that if this quantity behaves like square root of j, small o of square root of j, then a little bit of argument from measure theory allows us to show that the underlying sequence must converge almost everywhere. So in other words, it's a Cauchy sequence, and the L2 is a complete space, and we are done. So the circle method of Hardy and Litwood, this is some method, very powerful method in number theory, which was used by Hardy and Litwood to solve the Waring problem. Waring problem says that every sufficiently large integer can be written as a certain number of squares. And the circle method was used to quantify this phenomena, to give an asymptotic formula for the number of the solutions in the Waring problems. So, and that's a very analytical method. And Bourgain, he was a brilliant mathematician, and at that time he was involved in these problems in ergodic theory, and he knew everything, and he was able, to see that the circle method can be used, to understand the behavior of averaging operator on the Fourier transform side on L2, to understand, in other words, to use the Fourier methods and to pass to on the Fourier side with the operator and to say something reasonable. And that was his idea, and it was very powerful. And these papers where he solved this problem were acknowledged in his Fields Medal. So it was a huge breakthrough that he made. And now let me tell you a few words about the current state of the art. So Eva, how much time do I have? How can I?
Can you finish in 5 minutes?
Okay, I think so that I can. Yes, I think I can. Yes.
Please.
Okay, so let me tell you now that this is what is important now. It's understanding, asymptotic limiting behavior of this averaging operator as n goes to infinity, and norm or pointwise convergence. And what happens, if we consider, if it comes to the norm convergence, everything is essentially understood. So, and here we have the how everything was developed over the years. So in 1977, the bilinear version of this operator, when k is equal to, was understood for the linear polynomials. This is in particular, if you have a limit here of this operator, then we can deduce the Roth theorem using the ergodic methods. And then Furstenberg and Weiss, but before that, that was a fundamental paper of Bergelson in 1986, where he started to consider the polynomial configurations. He was able to say something for weakly mixing dynamical systems. And then Furstenberg and Weiss in 1996 tried to understand the situation where one polynomial is linear, the second one is quadratic. And they proved the norm convergence for this. And in 2002, and Horst and Krah, and in 2004, independently, Tammy Ziegler, they established norm convergence in Fourier generality for polynomial orbits and arbitrary k. And that are very deep papers. And this is a beautiful subject. And Sasha Liebman in 2005, he was able to extend the results of Horst and Krah and Ziegler to polynomial orbits. So that's what we have essentially, that's what we know essentially about the norm convergence. But now, the pointwise convergence at that time, that was the only in the bilinear setup. So that was the results of Bourgain from 1990, the bilinear situation, and two polynomials with linear polynomials, and for this operator we have pointwise convergence. And now this motivated Furstenberg, Bergelson, and Liebman to formulate the following conjecture: that if we consider a nilpotent group of measure-preserving transformations in a probability space and polynomials with integer coefficients, and the measure-preserving transformation will be taken from this nilpotent group of measure-preserving transformations, then it's expected that the following averaging operator converges almost everywhere as n goes to infinity. And in fact, now we know that the norm convergence for this operator is known. This is due to a beautiful paper of Miguel Walsh from 2012. This is the Annals paper, where he used the, in a very clever way, Hahn-Banach theorem to establish norm convergence for this operator on L2. But the pointwise convergence is completely unclear. And on the other hand, if we go beyond the nilpotent groups, then Bergelson and Liebman showed that L2 convergence, norm convergence may fail, as well as pointwise convergence. So therefore, the nilpotent setting is the best what we can say. And let me tell you that recently I was able, with my collaborators, to make some contributions to this conjecture. So recently with Ionescu, Magyar, and Szarek, we were able to show that if we have a sigma finite measure space and measure preserving transformations, which are taken from nilpotent group of step 2, which means that the following commutator relation is satisfied, then this averaging operator, linear operator, but with arbitrary polynomial orbits, converges mu almost everywhere as n goes to infinity. So That's one result in the linear setting. And there is also another result of mine with Ben Krause and Terry Tao, where we were able to extend the Bourgain pointwise ergodic theorem to show that the following bilinear averaging operator converge mu almost everywhere as n goes to infinity. So that's the in other words, this solves the problem of pointwise convergence for the Furstenberg-Weiss averages. Here, let me finally, because my time is running out, I extended about the ideas that we used in the proof of this theorem. So that there were several, deep results from the literature that we needed to establish this theorem. So that was something which is called the Ionescu-Wenger multiplier theorem, which is can be thought as a discrete Latewood-Paley theory and paraproduct theory. That are tools from harmonic analysis and number theory. The circle method of Hardy and Littwood, this is the number theoretical tool. The inverse theory of Peluz and Prendiville, this is from additive combinatorics and number theory. Hahn-Banach separation theorem from functional analysis, LP improving estimates of Hahn, Kovac, Lacey, Madrid, and Tille, which was a consequence of the Vinogradov mean value theorem. This is also a tool from harmonic analysis and number theory. And the Rademacher-Menschow argument combined with Khinchin's inequality. This is probability, functional analysis, harmonic analysis, the shifted square function, purely harmonic analytic tool, and bounded metric entropy argument from Banach spaces. This is also combinatorics, Fourier, functional analysis and probability. And finally, the van der Korput type estimates on p-adic fields. This is from harmonic analysis and number theory. That was a combination of a lot of tools. The paper has more than 100 pages, but ultimately we were able to establish the pointwise convergence in this context. And now we work on some more general extensions of this theorem. So I will tell you. So we are trying to understand the situation.
Mariusz, we have to stop because there might be some questions, and I
Sure.
need to take a colleague to the station. It's so I cannot continue forever.
Yeah, it's fine.
So
I'm sorry that I extended.
Thank you very much for the beautiful lecture.
Yeah, thank you so much for your attention. Thank you.
I'm
I'm sorry that I extended.
No, it's great. I wanted all of this to be recorded, but I'm kind of in a hurry. So, are there any questions? Quick questions, let's say, please, come here, David, and take mine.
So I don't know whether it is a good question, but somehow this Banach, this density of natural numbers is some sort of measuring how large is the set. So my question is there a way to extend it to maybe not sigma finite, but additive measure? Just finitely additive. Something like, for example, Banach.
I think that it is, because this can be used, to construct the Banach limit. I think there is some, as far as I remember, that you can use this. And okay, I have to think about this. I cannot tell you offhand.
Okay. Okay, thank you. And one quick comment: this number, which I was asking before, it's a product of consecutive prime numbers from 2 up to 23. So it's 2 times 3 times 5 times 7 times 11 and so on, up to 23. This coefficient.
Yeah. This is what I thought, that this is the double factorial. Sometimes it's used double factorial, right?
Oh, no, not all odd integers, only prime ones.
Prime.
So, for example, I omit 9 in this product.
Okay.
So.
Okay, perfect. Okay.
Thank you.
Okay, thank you.
Okay, David, please.
I wanted to ask about these arithmetic progressions that are looked for in some particular sets of natural numbers, and especially in the prime numbers. What are the applications of this in computer science, perhaps some cryptography.
Okay, I can. Okay, I'll tell you. I can't tell you about this. I have no idea. I only know that this is some people are fascinated with searching this prime the arithmetic progressions in the primes and trying to understand efficiency of algorithm and construct new algorithms. So this is what I know, that that was so because we have to start from something. So now we have the theorem that has existential nature, and now we can ask if we have some efficient tools to find this. But I can't tell you about any other applications. I'm not aware of.
Okay, because I thought that on one hand we need big prime numbers, right? But we don't want them to be easy to guess, right? Because they are.
Yeah, that's right. This must be much clever, how to do this, to find that the entire sequence. It's yeah, but I sorry, I can't tell you about any other application. I'm not aware of.
Sure, thank you.
Okay, any questions from people in Zoom?
Okay.
Zoom. Please just unmute yourself and ask a question. Okay, if not, let's thank Mariusz again.
Yeah, thank you very much for your attention. Thank you.
I will stop the recording.